Chapter 14 Interlude Memory API. In this interlude, we discuss the memory allocation interfaces in Unix system. The interfaces provided are quite simple, hence the chapter is short and to the point. The main problem we address is this: Grok's how to allocate and manage memory. In Unix and C programs, understanding how to allocate and manage memory is critical in building a robust and reliable software. What interfaces are commonly used? What mistakes should be avoided? 14.1 Section 14.1 Types of Memory. In running a C program, there are two types of memory that are allocated. The first is called stack memory, and allocation and deallocation of it are managed implicitly by the compiler for you, the programmer. For this reason, it is sometimes called automatic memory. Declaring memory on the stack in C is easy. For example, let's say you need some space in a function for the integer called x. To declare such a piece of memory, you just do something like this. The compiler does the rest, making sure to make space on the stack when you call in the function. When you return from the function, the compiler deallocates the memory for you. Thus, you just want information to leave beyond the core invocation. You had better not leave the dev information on the stack. It is the need for long-lived memory that we get to the second type of memory called the heap memory, where allocations and deallocations explicitly handled by you, the programmer. The heavy responsibility, no doubt, and certainly the cause of many bugs. And if you are carefully and pay attention, you will use such interfaces correctly and without too much trouble. Here is an example and how one might allocate the integer on the heap. A couple of notes about this small code snippet. First, you might notice that both the stack and the heap allocation occurs in this line. First, the compiler knows to make room for the pointer to an integer when it sees your declaration of a set pointer, and subsequently, when the program called memlog and immediately cast space for the integer on the heap, the routine returns the address of such integer upon success or on failure, which is then stored in the stack for use by the program. Because its explicit nature and because of its wide usage, and heap memory present more challenges for both users and systems. Thus is the focus on the remainder of our discussion. 14.2 The memory call. The memory call is quite simple. You pass it aside asking for some room in the heap, and it either succeeds and gives you a back pointer to the newly allocated space or fails and returns null. The manual page shows that you need to use memlog. Type memlog at the command line, and you will see. From this information, you can see that you need to do is to include the header, the file stream lib, the standard lib.h to use memlog. In fact, you don't really need to even do this. As a C library, while the all C programs link in by default at the code for memlog inside of it. Adding the header of just lets the compiler check whether you are calling the memlog correctly. For example, passing the right number of the argument to the of the right type. The single parameters the memlog takes is of the type size t, which simply describes how many bytes you need. However, most programmers do not type in a number here directly, such as 10. Indeed, it would be considered the poor form to do so. Instead, various routines and macros are utilized. For example, to allocate the space for the double precision floating point value, you simply do this like that. So, wow, that's a lot. That's a lot of doubling. The invocation of a memlog use the size of operator to request the right amount of space In C, this is a general result of the compile time operator, meaning that the actual size knows compile time and thus number, in that case 8 for the double, and substituted as the argument of the memlo. For this region, side of is correctly thought of operator and not a function call. A function call would take place at runtime. So the tip: when in doubt, try that. You are not sure how some routine operator you are using behaves. There is no substitute for simply trying it out, making sure they behave as expected, while reading the manual pages or other documentation is useful. How it works in practice is what matters. Write some code and test it. That is no doubt the best way to make sure that your code behaves as you desire. Indeed, this is what we did to double check the things we are saying about the size of were actually true. So you can also pass in the name of the variable as not just type to size of, but in some cases you may not get desired result. So carefully. For example, let's look at the following code snippet. In the first line, we've declined the space for an array of 10 integers, which is fine and dandy. However, when you use side of the next line, in terms of a small value, such as 4, on 32-bit machines or 8 on a 64 machines, the reason that in this case, the size of things we are simply asking how big a pointer to an integer is not how much memory we are having dynamically allocated. However, sometimes the size of it does work as you might expect. So in this case, there is enough static information for the compiler to know the 4 bytes have been allocated. Another place to be careful is the string. The vector in the space for string. Use the following idioms: memory allocation string length plus 1, which catch the length of the string using the function string length and in the adds 1 to the it. In order to make room for the end of string character, using side of may lead to trouble here. You might also notice the memlo returns a pointer to the type void doing so it's just way in the C to pass back in address and let the programmers decide what to do with it. The programmers further helps out by using what is called by a cast. In our example above, the programmer cast the return type of memory memlo to pointer to a double. Casting doesn't really accomplish anything other than tell the compilers and other programmers who might be reading your code, yeah, I know what I'm doing. By casting the result of the memlo, the programmer isn't giving some reassurance the cast is not needed for the correctness. 14.3. The free call. As it turns out, allocating memory is the easiest part of the equation. Knowing when, how, and even the if to free memory is the hard part. To free memory that is longer in use, programmers simply call free. The routine takes one argument, a pointer returned by the memlo, but you might notice the size of the allocated region is not passed in the user, and all must be tracked by the memory allocated library itself. 14.4 Common errors. There are a number of common errors that arise in the use of memlo and free. Here are some we've been over again in the teaching the undergraduate operating system course. All of these examples compile and run with nearly a pip from the compiler. While compiling a C program is necessary to build a correct C program. It is far from the sufficient, as you will learn, often in the hard way. Correct memory management has been such a problem. In fact, the newer languages have support for automatic memory management. In such languages, while you call something akin to memory alloc to allocate memory, usually new or something similar to allocate a new object, you never have to call something for free space. Let a garbage collector runs and figure out what memory you no longer have references to and freeze it for you. Forgetting to allocate memory. Many routines expect memory to be allocated before you call them. For example, the routine SR string copy, destination source, copies a string from a source pointer to a destination pointer, However, if you are not careful, you might do this. Like the oops, okay. So when you tip it compiled or it ran does not equal it is correct. Just because the program compiled or even ran once or more times correctly does not mean the program is correct. Many events may have this conspired to get you a point where you believe it works, but then something changes and stops. A common student reaction is to say or yell, but it worked before, and the brain of compiler operating systems. However, even there we say it and the professor, and the problem is usually right where you think it would be in your code. Get to work and debug it before you blame those other components. When you run this code, it is likely lead to the segmentation fault, which is fancy then for you did something wrong with the memory, you foolish programmers, and I'm angry. In this case, the problem code might instead of like this. The alternatively, you could use the string up and make your life even easier. Reader start a mint page for more information. Not allocating enough memory. A related error is not allocating enough memory, something called for buffer overflow. In the example above, the common error is common makes almost enough room for the destination buffer. Oddly enough, depending on how malloc is implemented and in many other details, this program will often learn assembling correctly. In some cases, when string copy executes, it writes one byte too far past the end of the allocated space. But in some cases, this is harmless, perhaps overwriting a variable isn't anymore. In some cases, this overflow can be incredibly harmful and a factor that the source of the many security vulnerabilities in systems. In other cases, the malloc live allocate the reader extra space anyhow, and thus your program actually does scribble on some other variable's value and works quite fine. In even other cases, the program will need it for a crash, and thus we learn another valuable lesson. Even though it ran correctly once, doesn't mean it's correct. Forgetting to initialize the allocated memory. With this error, you call malloc properly, but forget to fill in some values into your newly allocated data type. Don't do this. If you do forget, your program will eventually encounter an uninitialized read where it reads from the heap some data of a known value. Who knows that might be in there. If you're lucky, some value such that a program will still work. For example, 0. If you're not lucky, something random and harmful. Forgetting to free memory. Another common error is known as memory leak. It doesn't when you forget to free memory. In long-running applications or systems such as OS itself, this is a huge problem, as slowly leaking memory eventually leads one to run out of memory, at which point a restart is required. Thus, in general, when you're done with a chunk of memory, you should make sure to free it. Note that using a garbage-corrected language does help here if you still have a reference to some chunk of memory. No garbage corrector will ever free it, and thus memory leaks may remain a problem even in more modern languages. In some cases, it may seem like not calling free is reasonable. For example, your program is short-lived and it will be exit. In this case, when the program dies, the OS will clean up all of its allocated pages, and thus no memory leak will take place there. While this certainly works, say on the side of page 147, it is probably a bad habit to develop, so it we're wary of choosing such a strategy. In the long run, one of your goals as a programmer is to develop a good habit. One of those habits is understanding how you are managing memory, and in language like C, freeing the blocks you have allocated. Even if you get away from not doing so, it is probably good to get a habit of freeing each and every byte you explicitly allocate. The freeing memory before you are done with it. Sometimes the program will free memory before it is finished using it. Such a mistake is called dangling pointer, and it, as you can guess, has also bad things. The subsequent use can crash the program or override valid memory. For instance, you code free, but then use the memory cooking again to allocate something else, which then results in the warranty-free memory. Inside, why no memory is leaked once your process exists? When you write a short-lived program, you might allocate some space using malloc. The program learns and is about to complete their need for free a bunch of times just before it is exiting. While it seems wrong not to, no memory will be lost in any real sense. The reason is simple. There are really two levels of memory management in the system. The first level of memory management is performed by the OS, which hands out of memory to the processes when they run and take it back and when the process exists or the otherwise die. The second level of management is within each process. For example, within the heap, when you call malloc and free, even if you fail to call free and thus leak memory in the heap, the operating system will decline all the memory of the process, including those pages for code stack and as relevant here. Here, when a program is finished running, no matter what the state of your heap in your address space, the OS takes back all of those pages when the program dies, thus ensuring that no memory is lost despite the fact that you didn't free it. Thus, for short-lived programs, leaking memory often does not cause any operational problem, though it may be considered a poor form. When you write a long program server, such as a web server or a database management system, which never exits, leaked memory is a much bigger issue that will eventually lead to a crash when the application runs out of the memory. And of course, leaking memory is an even larger issue inside one particular program. The operating system itself is showing once again, those who write the corner code have the toughest job of all. Next is freeing memory repeatedly. Programs also sometimes free memory more than once. This is known as a double free. That the region of doing is so undefined. As you can imagine, the memory allocation library might get confused and so do all sorts of weird things. Crashes are a common outcome. Calling free incorrectly. One latest problem we discussed is the call of free incorrectly. After free, expect you only to pass it one of the pointer you received from the malloc earlier. When you pass in some other value and bad things can and do happen. Thus, such invalid frees are dangerous and of course should also be avoided. Summary. So you can see that there are lots of ways to abuse memory. That because of frequent errors with memory, while a whole ecosphere of tools have developed to help find such problems in your code. Check out the both Purify and the Valgrind. Both are excellent at helping you allocate the source of your memory-related problems. Once you become accustomed to using these powerful tools, you will wonder how you survived without them. 14.5 Underlying OS Support. You might have noticed that we haven't seen talking about the system calls when discussing memory and free. The reason for this is simple. They are not system calls, but rather library calls. That the malloc library manages space within your virtual address space, but itself is built on top of some system calls which call into the OS to ask for more memory or release some back to the system. One such system call is called BRK, which is used to change the location of the program break. The location of the end of the lead, it takes one argument, the address of the new break, and thus either increases or decreases the size of the heap based on whether the new break is larger or smaller than the current break. An additional code SBRK is passed an increment, but others serve a similar purpose. Note that you should never directly call either BRK or SBRK. They are used by the memory allocation library. If you try to use them, you are likely make something go wrong. Stick to the memory allocation and free instead. Finally, you can also obtain memory from the operating system via memcall by passing the correct argument to memcall. Memory mem can create an anonymous memory lesion within your program. A lesion which is not associated with any particular file but rather with the swap space, something we will discuss detail later on in virtual memory. This memory can then be treated like a chip and managed as such. Read the manual page or mem for more details. 14.6 Other codes. There are a few other codes that a memory allocation library support. For example, C allocates memory and also zeros before returning. This prevents some errors where you assume that the core memory is zeroed and forget the initialization yourself. See the paragraph on the uninitialized list above. The routine realloc can also be useful when you've allocated space for something, say an array, and the need to add something to each realloc makes the new larger region of the memory. Copy the old region into it and return to the pointer to the new region. 14.7 Summary. We have introduced some of the APIs dealing with memory allocation. As always, we have just covered the basics. More details are available as well. Read the C book and the Stephen Chapter 7 for more information. For cool modern paper on how to detect and correct many of these problems automatically, see the Norvag et al. And this paper also contains a nice summary of the common problems and some neat address on how to find and fix them. References. Homework.